Okay, so we've spent a couple of days talking about the disc method and then the washer method, which really is just the disc method, rotated around an axis other than one that it's touching. But today we're going to talk about rotating around the y-axis, and to do that we're going to use shells. So we're going to get back out our notes from 73. We skipped this example, so we're going to be talking about example 2. But I just wanted to remind you what we were doing with our disk. So with our disk method, we had this representation that we rotated around to create that disk. And then we were basically summing up the disk, like summing up a bunch of weights on a barbell, like summing up all of those volumes. But when we're using shells, what we're going to do is have that same representation, but we're going to rotate around the y-axis, which creates a cylinder. When you rotate this around the y-axis, you're going to get a cylinder shape. So I want to talk about that cylinder shape for just a minute and where our formula for using shells is going to come from. And then we won't really have to refer back to it. I just wanted you to know where it comes from. So if I have this shell, I think I'll put it right down here. So if I have just oh, my pen stopped working. So if I have this shell rotated around this axis, all right, and to the middle of the width here, I'm going to call that P, and then this is the width W. Then here's what I could say. If I were going to do this using the volume formula pi r squared h, I would have pi times p plus this little half right here. To get me to the outside, I would have to do half of w, so w over 2, so squared, times h. Now that would just be the outside, and h refers to the height here. So pi r squared, and r becomes this thing, h. And then we would have to take away this inside piece, which would be pi times p minus w over 2 squared h. So this would give me my volume. Well, you can multiply it out if you want, but when you multiply p plus w over 2, you get, actually I think I'm going to go ahead and take the pi and the h and factor that out to the front, so pi h to the front, times, and then when I multiply this out, I would get p squared plus pw plus w squared over 4 minus, so this is the first one, and then if I square this one, p squared minus pw plus w squared over 4. And then if I subtract those, I have my pi h times p squared minus p squared is gone. Pw minus a negative pw would be 2pw. And then w squared over 4 minus w squared over 4, that's gone. So I have pi, well, I'm going to put the 2 in front, 2 pi, and then hpw. Now let's talk about what each of these things represent. This 2 pi is just constants. The h, p, and w. The p is going to be the radius, just like we see here. It's how far out we're going to rotate. So like in this picture. Our representative radius is going to be our P of W. So function PW, and usually that's just going to be some x value, like we're going some distance x out. Now if they ask us to rotate around some other line, it won't just be x, but most of the time it's just some value of x. So this is usually just x. And then the h represents our height, which is going to be top curve minus bottom curve. And then this w is just our representative width, which is that dx. So we end up with 2 pi times p of x times h of x with respect to x. And we're going to take the integral from a to b. All right, well, I promise it's a lot easier to use than it is to understand what we're, the formula, where the formula is derived from. But hopefully this helps a little bit. We're just taking the outside minus the inside, and we end up with this formula. And so here's how that works in our example. So in our example, it said, find the volume, and this is example 2 on 73, of the solid generated by revolving the region bounded by the curve y equals x cubed the y-axis and the line y equals 3. And we're going to rotate this region around the y-axis, so it's going around this axis. Okay? So that's what we have represented in our picture here. And so they're taking this representation and we're going to rotate it around, which creates all these cylinders. So in this representation, like I said, this is going to be our P of W, or P of X. And so we're going to have our volume equals 2 pi times the integral, and we're still using x's, and so we need to know where these intersect. And remember, this is the line y equals 3, and this is y equals x cubed. So if we want to know where they intersect, we can just set them equal to each other. X cubed equals 3. So x is the cube root of 3, or 3 to the 1/3 power. So we're going to go from 0 to the cube root of 3. 0 to the cube root of 3. And then we're going to have our x, like however far we go out, which is some x value. And then for that x, we have a height that goes along with it, top curve minus bottom curve. In this case, 3 minus x cubed with respect to x. So this is the P of x, this is the H of x, and this is just that dx, or the W, the width. I guess I'll write width here. All right, so that's how it all fits into our formula. So we're going to put that back over here on our other paper. So again, I'm going to draw it out one more time. So we have this representation that we're rotating around our axis that creates this shell or onion effect. So it's a bunch of shells kind of stacked inside one another, kind of like the peel of an onion. And so this representation, we have some distance away from the y-axis, so some x value away. So we have our volume is 2 pi times the integral from 0 to where they intersect here, cube root of 3, of x times, and then the height of this representation is 3 minus x cubed. All right. Now, if you'll type this part into the calculator, we're going to get 2 pi times 1.872. And I'm going to go ahead and type that in so you can see it real quick. All right, so there's the part that we're integrating. And we're going to calculate the integral, number 7, from 0 to, and then the cube root of 3 is probably easiest to put in 3 raised to the 1/3 power. Oops. And that's at 1.872. And then we're going to multiply that times 2 pi, and we get 11.763. All right, so the volume that this generates right here. All right, we're also going to take a look at our notes 74, where we talked about the washers, but there was one that we skipped on here as well around the y-axis, and so we're going to take a look at that one right now so that we can see how to do that one using our shell method. So find these notes. You might want to pause this real quick, and we're going to take a look on the back at example 4b. So example 4, we had these two curves, y equals x and y equals x squared, so it was the same in all examples, but I'm going to go ahead and draw it one more time. All right, so we end up with this region right in here. And this time, we're supposed to rotate around the y-axis. So now our representation, remember this is going to spin around the y-axis. And so this whole shape spinning around the y-axis is going to create kind of a bowl shape with a V cutout in the middle. And so with all of our information that we put down on our other notes, we know that this is going to be 2 pi times the integral from intersection to intersection. In this case, it was 0 to 1 of our p of x, which in this case is just some distance x, times the height, top curve minus bottom curve. In our case, that's x minus x squared. So it's pretty easy to set these up, and then we just evaluate that on our calculator. All right, so here's our equation. We're going to calculate the integral. We're going from 0 to 1. So we get 0.083 repeating. So it's 2 pi times 0.083. And so I can pull that to my home screen, times 2 pi, and I get 0.524. We'll do the volume generated. Okay, I do want to show you one more problem using the shell method where we're not rotating just around the y-axis. So they could change this to some other vertical axis. And so in this problem I just made up, we're going to rotate around the line x equals 6, which is a vertical axis. But we're still going to use the shell method, and it's not much different. I just wanted you to see what it looks like. So here's what we have. This one we've got y equals 0. We've got the square root of x. Make it a little longer. We've got x equals 0, and then x equals 4. So it gives us this region bounded. And they want us to rotate it around the line 6, which is over here. So our axis of rotation is further away. There's a gap in between our region and our axis of rotation. There's not much difference in the way that we do this problem. we're still going to do our volume equals 2 pi times the integral. And remember, we still have this representation in here. And we still are going to use these intersections. So this is from 0 to 4 of p of x. Now, p of x in this problem is not just x, because we're not just going some distance away from here, from the y-axis x. We're going a distance from here backwards to that line. So p of x in this one would be 6 minus some x value. So that's what we're going to put here instead of just x, is our axis of rotation minus x, and then our height, which is the square root of x minus 0, or just square root of x. And that's the only difference. Whenever you're rotating around some other vertical line, this p of x value is going to change. It's not going to be just x. And then we can just type it in the calculator. Alright, so here it is, 6 minus x times the square root of x. We're going to calculate the integral from, oh, do I have 4? 1, 2, 3, 4, yep, 0 to 4. So we get 19.200. So we have 2 pi times 19.200. So I can pull that to my home screen. Times 2 pi. And I get 120.637.